Hello and welcome to Honors Function. In the next 3 lectures, we're going to continue looking at the zeros of a polynomial function, but this time we won't be thinking graphically. We won't look at the behavior of the graph, the local behavior around the x-intercept. We're going to develop some tools, some algebraic tools that sometimes allows us to determine the exact value of the zeros of a polynomial function. Let's begin with a definition. Let's start by taking two polynomials, p of x and d of x. We are going to call d a factor of p of x or a divisor of p of x if there exists a polynomial q of x such that q of x times d of x is equal to p of x. Okay? So you can think of the analogous definition about factor and divisor for numbers, right? You say that 3 is a factor of 15 or a divisor of 15 because there exists another number, 5, such that 5 times 3 equals 15, okay? And this is called a factor of 15 or a divisor of 15. So actually, very often in these 3 lectures, we will have some strong analogy between polynomials and integers. Okay? Let's continue with the first example of this definition. I do 1 and you do 2. So how do you show that d is a factor of p? Well, you know what to do, right? You take p of x and you're trying to find a polynomial that multiplies d to give you p. Well, the easiest way here is possibly to try to factor this. So it's telling me that this is 2x minus 1, so it's giving me some information already. So I'm going to say 3x right here. And if I want minus 8, it better be plus 8. So I hope this works. Let's see. Plus 16 minus 3 is plus 13. Yep, that's it. So this would be my q of x polynomial. Q of x is going to be called, of course, why did I choose the letter q? Because we're going to call it the quotient, okay? And then we're thinking the quotient. This is the dividend, and this is the divisor. So if you're thinking along these lines, you'll start talking about the division of two polynomials. How do you divide p of x by d of x, okay? Dividend, divisor, and you find the quotient. Well, this division doesn't have a remainder, just like above when I wrote, for example, that 15 equals 5 times 3. There is no remainder. I chose to divide 15 by 3. Now, what happened if you chose to divide 15 by 4? Okay, well, you will have a remainder. How many 4s in 15? You have 3 4s in 15, and the remainder is going to be 3. And this remainder better be smaller than the divisor. Okay? Here, let's go over another example with numbers. Suppose you have some marbles. Let's say you have 43 marbles, and you want to put them in some bags. You want to put 4 marbles in bags. Okay? How many bags are you going to have? Well, let's see. 4 marbles in a bag. If you say that you're going to have 9 bags with 4 marbles, what's going to be left? 9 times 4, 36. So you're going to have 7 marbles left. Well, that's not correct. You can still take 4 marbles out of the remainder right here and put them in another bag. So actually, with 43 marbles, you can have 10 bags, and the remainder will be 3. So you understand how the remainder is supposed to be smaller than the divisor, because if it's not smaller, you are not done. Right here, you can go further. The remainder is supposed to be smaller than the divisor. This is a division. This is the first type of division you study when you're very, very young. It's called the Euclidean division. Okay? Now, I'm not sure you have called it like that, but this is what it's called, Euclidean division. You have the dividend that is equal to the quotient times the divisor plus the remainder. This is what I give you in my notes in the next definition of the Euclidean division. Let's go over some examples. I'm going to let you do number 3 and I'm going to do number 4. So the question is this a writing for the Euclidean division? They don't tell you which one is a divisor. Maybe 7 is a divisor, or maybe 10 is a divisor. Okay, I don't know which one is a divisor, 7 or 10. But I can tell you this is not the Euclidean division, because 13 is above 7 and it's above 10, right? Okay, so if we consider that 10 is a divisor, then let's write the Euclidean division of 83 divided by 10. So I'm going to take 10 out of 13 and I'm going to give it to that. So it's going to be 10 times 8, right? You get one more package of 10. 10 times 8 plus 3. Now this is the Euclidean division of 83 by 10. Now, if you want to do the Euclidean division of 83 by 7, what are you going to do? You're going to say it is 7 times, so how many 7? You take a 7 out of that and you give it to, you make one more package, right? So it's going to be 11, and what's going to be left? You're going to have 6 left. And this is the Euclidean division of 83 by 7, okay? So 2 different writing, and 6 is smaller than 7 and 3 is smaller than 10. Okay, so why did I review the Euclidean division between integers? Because we have the analogous operation between polynomials. So let's look at the result. But before we do so, let's just notice something here. I take 83, and if I want to divide it, then my divisor has to be smaller than 83, right? This is the Euclidean division. It's between integers. We do not have rational numbers, okay? I'm not looking at 7 over 10, for example. You cannot divide 7 by 10 if you're only dealing with integers, right? You can divide 10 by 7. 10 equals 7 times 1 plus 3, but you cannot divide 7 by 10, okay? I just want integers here. So what's going to play the role of this? This number has to be bigger than this number. What's going to play the role of that when we look at polynomial? Let's look at the result. So here is the result, and what plays the role of bigger than is the degree of the polynomial. If you take a polynomial p of x whose degree is greater than or equal to another polynomial, then you can divide p of x by d of x, okay? And that means you can find 2 polynomials, q and r, quotient and remainder, such that p of x equals d of x times q of x plus r of x, right? And the degree of the remainder has to be strictly smaller than the degree of the divisor. If it's not smaller, you are not done. So now hopefully you understand why I reviewed division of integers, because it has the same flavor, okay? Let's go over the first example. So I'm going to do number 5 and you're going to do number 6 and 7, please. Let me show you how the long division, so-called long division or Euclidean division of polynomials work. All right, let's see. I want to divide this polynomial p of x, degree 5, by this polynomial degree 3. So already the degree works, so I can do that. So let's see. X cubed plus x minus 2 divided by 2x5 plus 3x cubed minus x squared plus 1. Now, hey, listen, if you have done that last year, I know teachers sometimes go over like holding position, leaving some places empty because of degree. Well, guess what? I don't do that, okay? I don't do that because you don't need to. I'm just gonna show you what it is. This is like a trick, but it sometimes hides what's going on, and I don't like to hide anything that's what's going on, especially when it's super easy, okay? So let's divide this. First question, how many x cubed into 2x5? Another way of asking that is, what do you multiply x cubed by to find 2x5? Well, you're gonna multiply by 2x2, right? 2x2 times x cubed equals 2x5. Okay, now what? Now what do you do when you have found a number here? You multiply 2x2 by the entire divisor, right? So 2x2 times x cubed is 2x5. 2x2 times x is 2x cubed plus 2x2 times negative 2 is negative 2x, negative 4x2. Here we go. That's what you do. I multiply the entire divisor by 2x2. Next, what I need to do is subtract this polynomial from the dividend. From this, I need to subtract. So be careful here with your sign, okay? You are subtracting, all right? So I advise you to switch the sign right away. So for example, here so I'm going to turn it to a plus, minus, then this one turns into a minus, and this one turns into a plus. Now, this is not very clean, and I'm going to show you on the next line what I really do, okay? But let's do that. So, of course, this cancel. There's no more x5. X cubed, what do you have? Plus 3 minus 2, that's x cubed, right? Just 1 x cubed. X squared, what do you have? Negative 1 plus 4, that's plus 3x squared. Here we go. You don't have any x's, and therefore you only have 1 left. Here we go. I know some teachers sometimes they don't bring down the 1. Hey, that doesn't make any sense. I'm doing a subtraction of two polynomial, right? This one minus that one. You don't just keep some stuff out. This is like it's a salad, and it doesn't make sense. Okay, I'm subtracting two polynomial. That's what I do. All right. Next, how many x cubed into x cubed? Well, that's easy. That's 1, right? So plus 1. So then what I'm going to do right here, I'm going to change my sign right away. Check it out. 1 times x cubed is normally plus x cubed. So right here I'm writing minus x cubed. 1 times x is plus x. So I'm writing minus x. 1 times negative 2 is minus 2. So I'm writing plus 2. You see what I did? I changed my sign right away. Therefore now I can just add instead of subtracting, okay? So I don't have to do these things that is not very clear right here. I'm just adding. No x cubed. 3x squared doesn't add with anything, so it's going to be 3x squared. 3x squared minus x, right? These two cancel. Plus 3. That's it. That's how you add two polynomials. And this is your remainder, okay? Therefore, the division is 2x5 plus 3x cubed minus x squared plus 1 equals the divisor, x cubed plus x minus 2 times the quotient, 2x squared plus 1, plus the remainder, 3x2 minus x plus 3. And this is how you have to write the results of your division with something that makes sense, okay? This polynomial, I wrote this polynomial, the dividend, as a product of two polynomial plus another one, okay? This is what makes sense. All right, please go over 6 and 7. Let's continue the lesson. So this is how I would like to see you writing the result of your division. But sometimes I need to show you another result because I think the book does that sometimes. Sometimes it's written in another way. So if you take this equality and if you divide both sides by d of x, let's see what you have. If you divide both sides by d of x, you will see the result written as p of x divided by d of x equals q of x, that's a quotient, right? You simplify, and then plus r of x divided by d of x, okay? This is another way to write it. I'm not a fan of it, and I will tell you why. At this point, it's too early to write it like that, because what is this? I don't know what that is. This is not a polynomial, right? And we are studying polynomials, therefore I have to stay in the set of polynomials. For example, let's divide 15 in 6. So it's 6 times 2 plus 3, right? Okay, so these are integers. Let's divide both sides by the divisor, by 6. 15 over 6 equals 2 plus 3 over 6. Now, if you're only working with integer, these numbers for me don't make any sense. What is 15 over 6? It's not an integer. It doesn't exist. In the set of integers, what would I do with this? It's senseless, okay? And that's the reason why I write my polynomial division just like that, all right? But you may see that. Now that will make sense when we're going to be talking about rational function. Of course, this will make perfect sense, just as when you talk about rational, this is completely fine, okay? Okay, let's go over the remainder theorem. You will see it's very, very simple. All right, let's take two polynomials, p of x and d of x, such that the degree of p is greater than or equal to the degree of d. So you can do the Euclidean division, and we would write p of x equals d of x times q of x plus r of x, with the degree of the remainder strictly smaller than the degree of the divisor. Okay, that's very, very important. Now, if you assume, so here's a polynomial p of x, and if you assume that d of x is just x minus a, okay, for example, x minus a. What is the degree of d of x? The degree of d of x is just 1, right? Okay, so you're going to write your Euclidean division, so let's write it. We have p of x equals d of x, so x minus a, right, times, we would find a quotient, q of x, plus a remainder, right, plus r of x. But now, the Euclidean division is telling us that the degree of the remainder has to be strictly smaller than the degree of the divisor. And the degree of the divisor is 1. What kind of degree is strictly smaller than 1? A degree has to be positive or equal to 0. You remember the degree of a monomial, right? Natural number or 0. So what kind of degree is strictly smaller than 1? Well, it's got to be 0. So the degree of the remainder has to be 0. What do we call a polynomial of degree 0? So the remainder is actually a constant number. That's a polynomial of degree 0, right? It's a constant number. So with that in mind, let's rewrite the Euclidean division. We have p of x equals x minus a times q of x plus a constant, right? The remainder theorem is telling us what is this constant. This is an equation that is true for any x, okay, true for any x. In particular, it is true, it is true for x equals a. What happens if you take x equals a? You have p of a equals a minus a times q of a plus k. A minus a, that's 0. So the product right here is 0, and you have k equals p of a. Okay, guys? And so this is the remainder theorem. Very, very important. If you're taking a polynomial p of x, and if you divide this polynomial by x minus a, then you're going to find a quotient, of course, and your remainder is gonna be p of a. That's gonna be your remainder, p of a, okay? This is called the remainder theorem. Now in math, we often divide polynomials by something that will look like this, like x minus 2, x plus 5, in this case is negative 5, right? X minus negative 5, x plus 1, you know, all these things. We often do that, and there is a shorter way to do the division. If you do that, you can do the division in a much faster way. It does come from the long division. I don't want to explain this in this video, but if you look at my notes, I even color-coded the long division to understand where the coefficient in the synthetic division, that's how it's called, the synthetic divisions are from. So please look at my notes, check out how it all collapses, how the long division completely collapses to give a synthetic division. It's a little bit faster. Let me show you how it works. So suppose you want to divide p of x, this polynomial, by d of x, x minus 3. Instead of doing the long division, you can do a synthetic division. Let me remind you right now how to do this. You have to write a right here, right? That's a equals 3. Then I have to write all the coefficient of p of x in the top row, so 5, negative 2, negative 3, 0, okay, this is for x, right? 0, you have to write them all, okay, and then 5, okay, and this is actually a degree 4 right here, all right? Then what? Then you bring down the first coefficient, you bring down 5 right here, okay? And every time you go back up, you multiply by this number. 5 times 3, 15, and now you just add, okay? Negative 2 and 15, 13. If you go back up, you multiply by 3. 13 times 3, 39. 39 plus negative 3, 36. 36 times 3, 108. Plus 0, 108. Times 3, 324. 324. Plus 5, 329. Now, of course, then what? You're done with the synthetic division, but you better understand what you wrote here, okay? So this is where you read your quotient right here. How do you read it? Well, if you start with a degree 4, this one is going to start with a degree 3, right? So the quotient is going to be 5x cubed plus 13x squared plus 36x plus 108. Where's your remainder? This is your remainder right here. This is how you read the remainder. And you know what the remainder is, right? The remainder is actually f of 3. So I know that f of 3 is actually 329. So not only I can find the quotient and the remainder, but the synthetic division allows me to quickly find output of a polynomial. Quickly find the output of the polynomial, and that's the other use of the division, okay? For example, what is f of 3 right here? You can quickly find it with the synthetic division by doing just some addition and multiplication. And that's why sometimes the synthetic division is also called synthetic substitution. Okay? Alright, I'll do example 8 and you will do example 9. So what is the remainder of this division right here? Well, I divide, so I'm going to call the top polynomial p of x, right? And I divide p of x by d of x, and I know that my remainder, according to the remainder theorem, is supposed to be p of negative 1. That's it, that's my remainder. And p of negative 1 is what? 2 times negative 1 to the power of 119 minus 8 times negative 1 to the 76 plus negative 1 to the 24 minus 13. So what is that? Negative 1, that's so it's negative 2, right? Negative 1 to an odd power is negative 1, and to an even power is 1. Minus 8 plus 1 minus 13. So negative 2, that's negative 23, negative 22. Okay. It's a little bit long, this video, but very important. Thank you for watching.